Hello and welcome to Lecture 3 of A Taste of Quantum Physics, the dreams stuff is made of in Phys 1201. In this lecture we're going to finish looking at why it is that the spectrum of a gas generally consists of discrete lines. You may not be entirely clear what I mean by a spectrum, but in fact you've seen them plenty of times, because that's all a rainbow is. When you take light and you split it up so that you see all the different colors that it's made out of, that's a spectrum. And you know that different colors correspond to different frequencies or different wavelengths. When you take white light, you get the familiar rainbow of all the colors. And you can do it in the lab as well with a prism, or even better with a diffraction grating. But of course, not all sources of light make white light. And in particular, when you take a gas and you run a current through it, an electrical current, you can make the gas glow. So the gas is producing light. And when you examine the spectra of different gases, what you see is that instead of a continuous rainbow of all the colors, only certain colors are present, and so you get lines in the spectrum. You're familiar with neon signs. You see that the neon spectrum has a lot of red lines in it, and so when you make neon glow, you see red. A lot of street lights use sodium in them, and so the familiar yellow of street lights comes from the fact that the sodium spectrum has two bright yellow lines in it. We're going to look at how you get lines in a spectrum by actually deriving a spectrum for about the simplest system we possibly can. So this is a system called a particle in a box, and it's just what it sounds like. You have a particle, and it's moving around inside a box. Now you can do this in 1, 2, 3 dimensions, whatever. We're going to stick with 1 dimension because it's simple. So our particle is forced to move along the x-axis and the x-axis only. And by a box, we mean that there are walls and the particle cannot get out through the walls. As long as it's inside the box, there are no forces on it, although I'll warn you, force actually is a problematic idea in quantum physics. The main thing here is that it is trapped between the walls of the box. And this sounds really abstract, except that it's actually a pretty good description for several real-life systems. The examples are conjugated pi systems. So here's an example. This is the beta-carotene molecule, and the electrons in this chain of alternating single and double bonds are free to move basically anywhere along the chain. They can't leave the chain, but they're free to be anywhere in it. And so that's kind of like a particle in a box. And another example is something called a quantum well, which are actually built in electronics quite often. When you sandwich one material between two other materials, you can arrange it so that the electrons in the material are trapped in this sandwiched material. Now we need to talk about probably the strangest and least understood idea in all of physics. It's the idea of a wave function. So de Broglie proposed that particles in some sense are waves. They have wavelength, and so in some sense they're waves. And we talk about them as having a wave function, or perhaps being a wave function. If this is sort of unclear to you, it's because it's unclear to everyone. This theory works really, really well. We know how to use it to calculate all sorts of things, but certain parts of its meaning are not clear to anybody. Anyway, here we go. So we're going to think of this wave function as just like a wave on a string. And so just like a string, it can't have any gaps or jumps. Also, we're thinking of this as telling us something about where the particle can be. So the wave function has to be 0 anywhere where the particle can't be. And now we know enough to put together what the wave function of a particle in a box should look like. It should be 0 at the walls or outside the walls because the particle can't be there. It can only be between the walls. And in between the walls, it has to look like some sort of wave. But there can't be any gaps or jumps, and so that wave has to have values of 0 at the edges so it joins up with the parts of the wave function outside the box. And it is a wave. We have to think of it as moving, but notice that it's restricted to be 0 at the walls So those are nodes. It's going to look like a standing wave. This next part should give you a really strong, spooky sense of déjà vu, because it's going to be just like our discussion of standing waves earlier in the term. So here are the walls of our box and the particle in between them. And let's say the length of our box is some L. Then there are allowed shapes for the wave function. It has to have zeros at the ends. And so the longest possible wave function is going to look like this, where here this is at 2 times, right? I'm showing it just like we showed standing waves earlier. And so if it looks like this, that's a half a wavelength in between the walls, and so half a wavelength is the length, and that gives us our wavelength. And then the next possibility is like this, where the wavelength is equal to the length, and so on. And so we get the same sort of pattern that we saw for a standing wave on a string, where you have these allowed wavelengths that go like this. So now we know that for the particle in a box, there are only certain allowed values of its wavelength. But we also know from the de Broglie wavelength that the wavelength is related to the momentum of the particle. And so if it's only allowed to have certain wavelengths, that means it's only allowed to have certain momentums. And we can find them easily. We just set the de Broglie wavelength, and I'll call this the nth allowed momentum, is just like so. All I've done is set this lambda equal to this lambda, which means we can now solve for the allowed value of momentum, and it's just going to be like so. Well, the final thing we can do is that we can realize that when the particle is in the box, there are no forces acting on it, so it has no potential energy. And so all it has is kinetic energy. But I'm going to rewrite that in sort of a strange way because it's going to be convenient. I'm going to multiply and divide by m. And the reason I've done that, I'll point out, is that mv is the momentum. And so this m squared v squared here is p squared. And so this is another way of writing kinetic energy, p squared over 2m. Well, I can just plug this expression for p into that, and I'm going to get that the nth allowed energy now, right? If it only has certain allowable momentums, it only has certain allowable energies, and so it's just going to be 1 over 2m, and all of this stuff for p squared, or in other words, what we have now are the allowed values of energy for a particle in a box. So, now we know that our particle in a box has only certain allowed values of its energy, which are given by this formula. And you'll often see this summarized in a diagram that looks like this. We call this an energy level diagram because we call these allowed energies energy levels, or states. And a bit of other terminology you'll come across is that the lowest energy state is called the ground state, and all the higher ones are called excited states. Well, now let's finally see why it is that things like molecules and atoms and particles in boxes have lines in their spectra. We have to look at how this particle in a box emits light. So let's suppose that we have this particle in a box in an excited state, say the n equals 3 state. How did it get there? I don't know. We've given it energy somehow. Maybe we ran a current through it, or we hit it with some light, or something like that. But it's in its excited state. And I'm going to draw the particle on that level in the energy level diagram. And now, things in their excited states tend to want to fall back towards lower energies. So let's say this is going to make a transition down to its n equals 2 state. And so there's a change in the energy of the system. Well, quantum physics may be weird, but one thing about it that it never does is violate conservation of energy. Conservation of energy is still an inviolable law, even in quantum physics. So if the system loses energy, that energy must go somewhere, and where it goes is into light. As the system falls back towards a lower energy state, it emits a single photon, and that photon has the same energy as the change in energy of the system. But now we can see why this system would have lines in its spectrum, because it's only allowed to have certain values of its energy. And so it can only emit photons with certain energies because those photons have to match up with differences between the energy states of the system. And we know that those photon energies all correspond to different frequencies or wavelengths of light. Well, let's finish up with a calculation. Let's say we have a quantum well. So this is one material here in yellow, sandwiched between two other materials here in pink. And this is used in things like diode lasers that you find in laser pointers and CD players and things like that. So this quantum well is 5 nanometers wide, and the electrons that are trapped in this material are going to behave like particles in a box. So let's find the energy of the ground state. That's going to be a good start if we want to know what wavelength of light we're going to get out of this. So E1, that's just going to be h squared over 8ml squared, right? So h 6.626. We're talking about electrons trapped in the well, and so this is the mass of an electron that we should use here. And now we just put the length of our well in. And we should check units. We have joule seconds all squared over kilogram meter squared. Well, a joule second is a kilogram meter squared per second squared times a second, and so it's a kilogram meter squared per second. And so here we have all of that squared. So kilograms squared meters to the 4 per second squared, all over kilogram meters squared. And so we're left with kilogram meter squared per second squared, and so we're going to get joules, as we should. So now I'm just going to plug all that into the calculator. And I get an energy of about 2.4 times 10 to the negative 21 joules. So that is the ground state energy. That tells us that if we're looking at the transition from n equals 3 to n equals 1, that's our final energy, our initial energy E3, well, that's just going to be 9 times that, right? Because all we do is we take that ground state energy and multiply it by n squared, which is 9. So that's easy. 2.2 times 10 to the negative 20. And so our energy of our photon is just equal to that delta E, or 1.9 times 10 to the negative 20. And now we can solve for the wavelength, because that energy of the photon is hf, or hc over lambda is going to be more useful to us here. And we get 1.04 times 10 to the negative 5 meters, or 10.4 micrometers. So that is in the infrared range and tells us that this quantum well is going to emit at this wavelength in the infrared. Among others, there will be other transitions that are possible, and so its spectrum would have a number of lines in it, but one of them would be a line corresponding to light of this wavelength.